Welcome to PALS. It's Prosanium's Anatomy Lecture Series. This is the part 2 of our study on limbic system. In the first part of our lecture, we looked at the cortical components of limbic system. In this second part, we'll look at the remaining part of the lecture. If you're just joining us, you're watching our video for the first time, we would love you to be a part of this great anatomy family where we make anatomy simple. So let's go to class. In this lecture, we'll be considering all the subcortical regions of the limbic system. And we're going to start with the amygdaloid nuclear complex. This is also called the amygdaloid body, or simply amygdala. Now, we're going to start with the bigger picture here. Here, this is the amygdala. And it's a very tiny structure, but very active, the neural activity. And in this other picture, this is also the amygdala. The amygdala is one of the subcortical components of the limbic system. It's actually one of the cells that is seen in the basal ganglia. It's armored in shape, and it is seen lying in the temporal lobe, close to the temporal pole. Let's use the next diagram. This is the amygdala, and here is our temporal lobe. It is located below the rostral part of the parahippocampal gyrus, and posteriorly, it continues as one of the other nuclei seen in basal ganglia, that is the caudate nucleus. So it continues posteriorly as a caudate nucleus, and also it continues as its major efferent, which is the stria terminale. Let's also appreciate this in the next image. Here is also the amygdala, and then continuing posteriorly here is the tail of the caudate nucleus. It will also run as its major efferent, which is the stria terminale. The amygdala has a number of connections. As a result of its activity, it receives several afferents from various parts of the brain, beginning from the cerebral cortex, the hippocampus, hypothalamus, the thalamus, even the midbrain. This image shows us the amygdala and then the various areas that we've just mentioned that it gets its afferent connections from. The major efferent for the amygdala is through the stria terminale and then the ventral amygdalofugal root. Here is our amygdala, and this is the stria terminale. It gives connections to one, the habenular nucleus, which is seen in the epithalamus through this fiber that is called the stria medullary thalami. It will also give connections to these other structures, one to the hypothalamus, the anterior portion of the hypothalamus. It also gives connections to the septal region, and then here is to the anterior commissure. Presently, we'll give a general constitution of the functions of amygdala. It plays important role in smell-mediated sexual behavior, and its stimulation will produce fear, emotions, anger, aggression, and release of hormones. We'll see more details before the end of this lecture. We have a syndrome associated with amygdala and some of the structures at the level of the temporal lobe, and then one of these syndromes is called Kluver-Bucy syndrome. Kluver-Bucy syndrome will arise as a result of bilateral temporal lobe lesion involving amygdala and adjacent structures. This results in marked changes in feeding behavior, abnormalities in sexual behavior, and some of the clinical signs include hyperphagia, which is compulsive eating, hyperorality, examining objects by putting them in the mouth, hypersexuality, heightened libido, visual agnosia, amnesia, and docility. We will look at the next part of the limbic system. And in this part, we'll be considering the fibers that actually connect the various cell bodies we have mentioned in the course of this lecture. We will take them one by one. Now, the stria terminale. In the course of this lecture, we noted that the stria terminale is the major efferent for the amygdala. This bundle begins in the amygdaloid complex and runs backward medial to the caudate nucleus. Now here is the amygdaloid body, or amygdala, and then we know that posterior to it is the tail of the caudate nucleus, and here is the stria terminale, that stria terminale running behind the thalamus here. So it runs and then gives its distribution to the septal area. This is the distribution to the septal area. It also gives its distribution to the hypothalamus. This is the distribution to the hypothalamus. And then it also gives a distribution to the habenular nucleus towards the posterior part here. And this is through the connection called the stria medullaris thalami. We'll consider the anterior commissure. In this image, this is our corpus callosum. This is the rostral part of the corpus callosum. Now, below the rostral part, we see this structure here. This structure is a structure called the anterior commissure. It's a rounded commissure. It lies behind the lamina terminalis. Here is the lamina terminalis. Here is the lamina terminalis. And here is the anterior commissure lying behind it. Now, it runs transversely in front of the anterior column of the fornix. Here is the fornix. Here is the fornix. This is the anterior part. And here is the anterior commissure. This commissure interconnects the middle and inferior temporal gyri, and most especially, it connects the olfactory regions of the two hemispheres. Now we look at fornix. As we already noted, the fornix is the major efferent for the hippocampus. The fornix is mainly a projection fiber which connects the hippocampus with the mammillary body seen in the hypothalamus. This is the fornix. This is the fornix. We have one on the right, one on the left. So this is the fornix. This is the fornix with the rest of the structures in the brain. Now here in this other image, we have extracted only the fornix so we can appreciate the various features of the fornix. Now it constitutes the sole efferent system of the hippocampus, and it is seen as an arched prominent bundle. We see the arched nature of the fornix, and it is seen below the corpus callosum along the lower border of septum pellucidum. Here is the corpus callosum. This is part of the septum pellucidum, and this is the fornix lodged below the corpus callosum. There is one fornix on each cerebral hemisphere, but the two are so closely related and fused together at the middle of the body of corpus callosum that we usually describe it as a single structure. Well, let's look at this information in the next image. This is the right fornix, and that's the left fornix. And then this is the part, this is the body of the fornix. And then we look at this part where they come together and as a result, seen as a single structure. The fornix originates from pyramidal cells of the hippocampus, and these cells will form the thin layer of white fibers that are seen on the ventral surface of the hippocampus, which are called alveus. Now, we also noted earlier in the lecture that the alveus will collect together on the medial margin of the hippocampus to form the fimbria, and then will run posteriorly as the fornix. How does the fornix get formed? One, this fimbria will move posteriorly and become rounded, and then will arch over the thalamus, which you see at this region, and across here with the opposite thalamus, they will form the body of the fornix, and then will join as a single structure, and then will move anteriorly and downwards. In this anterior part, the fornix will divide into two parts, into two columns, the right anterior column and the left anterior column. Each column will now arch downwards, as we noted here, and they will form what is called the post-commissural fornix, this part, as they move down to the hypothalamus. How is the fornix distributed? Now use this image to discuss it. One, some of the fibers of the fornix will move and go to the septal area. So these fibers that move to the septal area, because they've not passed beyond the anterior commissure, these fibers will be called the precommissural fibers. So the precommissural fibers will move to the septal area. Now we have the fibers that go to the hypothalamus that will go below the anterior commissure. So these fibers that go to the hypothalamus are called the postcommissural fibers. Now we have other fibers that will move to the splenium of the corpus callosum that will join the other fornix, and those fibers are called the commissure of fornix or hippocampal commissure. We also have fibers that will move from the splenial region of the corpus callosum and move upwards to join the cingulate gyrus. Those ones will actually form the association fibers. Looking at the distribution of fornix, we can classify the fornix as both projection fiber, commissural fiber, and association fiber. The fornix is basically a projection fiber. The fornix projected to the hypothalamus. That is its main function as a projection fiber. We also see it connecting with the opposite fornix, that is commissural fiber. And then we also see it moving upwards and connecting to the cingulate gyrus of the same hemisphere, and that is association fiber. Now for the mammillothalamic tract, these are fibers that will be running from here. This is the mammillary body in the hypothalamus. We see some set of fibers that will be running from this mammillary body to the thalamus here. And in the anterior part of the thalamus, the nuclei we call the anterior nucleus of the thalamus. So these fibers running here are called the mammillothalamic tract. Before we round off this section on the bundles of the limbic system, we would like to discuss a specific circuit, the Papez circuit, which is a circuit that controls emotional expression, actually named after the man that discovered it, James Papez. Now, the Papez circuit is a fundamental component of the limbic system. It's a closed neural circuitry that starts and ends in the hippocampus. Now, it connects the hypothalamus to limbic lobe and gives the basis for emotional experiences. Now, the Papez circuit includes the following structures: the hippocampus formation in the temporal lobe of the cerebrum, to the mammillary body here, mammillary body in the hypothalamus, 3, the anterior nucleus of thalamus in the thalamus, the cingulate gyrus in the cerebrum, the entorhinal cortex within the parahippocampal gyrus, and back to the hippocampal formation. It is concerned with short-term memory. The connections, this circuit starts from the hippocampus, and then from the hippocampal formation, it will connect to the mammillary body, and this connection is via a fiber called the fornix. From the mammillary body, the mammillothalamic tract will connect to the thalamus, and that's the anterior nucleus of thalamus. Now here, the anterior thalamic radiation will connect to the cingulate gyrus, and then the cingulum will connect from cingulate gyrus to the parahippocampal gyrus, but specifically the entorhinal cortex. And from here, it goes back to the hippocampal formation. Disorders of memory and behavior. Now for these structures that we've listed here, ranging from the hippocampus to the fimbria of the hippocampal formation, the fornix, the fiber, mammillary body in the hypothalamus, mammillothalamic tract connecting the hypothalamus to the thalamus, the anterior nucleus of the thalamus, and the cingulate gyrus. Any lesion along these structures can lead to defects of memory and also certain behaviors. In the beginning of this lecture, we connected amygdala to feeding behavior. How does amygdala do that? Now, amygdala connects to the hypothalamus, and we know that connection. This is through a fiber, which is the stria terminale. Now, in the hypothalamus, we have 2 nuclei that are responsible for our feeding. What are those nuclei? The ventromedial nucleus for satiety and the lateral hypothalamic nucleus for hunger. Now, because amygdala controls our feeding behavior, per time depends on what the feeling is. If the feeling is feeling of satisfaction There's no need for food. You're not feeling fine. Now, the nucleus that will be activated will be the ventromedial nucleus, which is for satiety. Or maybe the system, the GIT, the stomach is feeling, we are filled up. There's no more space. Now, it is the ventromedial nucleus that will be activated by amygdala. Then, lateral hypothalamic nucleus is the nucleus that's activated when there's need for feeding. And then when we have problem with amygdala, this hypothalamic nucleus is unleashed, and that is why hyperphagia is one of the indications of lesions in amygdala. We also noted that amygdala controls our sexual behavior. How does amygdala do that? Now, amygdala also connects to the hypothalamus through the same strata terminally. In the hypothalamus, we have two nuclei that control sexual behavior. One, we have the paraventricular nucleus, and two, we have the medial preoptic nucleus. The paraventricular nucleus will release oxytocin, which in men will increase sex drive. The medial preoptic nucleus will release gonadotropic releasing hormone, which will stimulate the release of testosterone, which also increases sexual libido. So when the message to amygdala is to activate the sexual behavior, this nuclei will be activated, and then these hormones will be released, and our sexual activity will also be increased. This is also the reason hypersexuality is associated with lesion of amygdala. Amygdala is also involved in our motivational behavior. How does amygdala also affect our motivational behavior? Now, it has connection with hypothalamus and septal area. Both areas, that's hypothalamus and septal area, will communicate with the part of the midbrain, a specific part of the midbrain, the ventral tegmental area, which will release dopaminergic neurons. And this is done via two pathways, the mesolimbic pathway and the mesocortical pathway. The mesolimbic pathway will stimulate the nucleus accumbens, while the mesocortical pathway will stimulate the nuclei in the prefrontal cortex. Both nuclei will trigger the reward feeling. Before we round off this lecture, I want to look at the limbic lobe disorders. Studies have shown that alcohol abuse and associated dietary deficiency of thiamine, that is vitamin B12, can lead to limbic lobe disorders. Here we see capillary hemorrhage in the upper brainstem and limbic structures. The patient will fall into confusion and coma, and this condition is called Wernicke's encephalopathy. Sometimes the patient can recover with a lot of disabilities. That's Korsakoff's psychosis. Here the patient may recover, but unable to remember previous experiences, that's retrograde amnesia, or to learn new facts, which is known as anterograde amnesia. We have come to the end of our lecture in the limbic system. We hope this material is useful. If you enjoyed this material, we would like you to please press the like button, share our video, and be part of this great anatomy family where we make anatomy simple. Thank you, and see you in our video.